Hey everybody, it's me! Live from the classroom. You know, live from the classroom. Homeworks. You got a lot of questions. I got a lot of answers in video form. Let's go through this. Let's wind the way through this. Let's go through it the way I think you might. So we read this. We got a satellite, orbit, unknown planet. So the first thing I'm thinking, so I'm going to have a diagram, right? So I got my planet, which I'll label with a P. Okay. And then I got a satellite, right? And I got two of them, so I'm going to call this S1. And this satellite's going like way in orbit like this. And I got a second satellite. It's at a different orbit going around like this, right? Around that planet. And I know the first satellite, I know it's moving at a speed, maybe V1, right? And things I also know in the problem, right? I know this distance, maybe we call this R1. I know this distance here, which maybe we call R2, right? Working with that. And then, so they're both circular orbits, and I know where they are, and that's all I really got, right? So if they're asking me for what's the orbital speed of the second satellite, satellite number 2 is where I'm working. So if I were to think about this, right, the second satellite here, the FBD for this is very simple. For both of them, it's really just FG acting. So I can make FBDs if I want, but if I think about the second satellite here, right, F net on the second satellite, well, that's going to be caused by the force of gravity. It's a gravitational attraction that's doing that. But what's special about this problem is that it's also in circular motion, so mac and cheese. Fun fact, I actually had meatloaf for dinner. I know it's different, but I was... Okay. So I got gravity that's causing this. So now, and then just a little pause here, right? This M being unlabeled, I don't feel comfortable with that. I'm going to put a little S on here, because for circular stuff, Mac, the M is always the mass of the thing going in a circle, not the thing making the circles happen. So I got this, and what I want to do with these, like we do so commonly, is set these two equal. So I would have FG, and then this is the mass of the satellite, and then this is the second satellite, but they're the same, so we don't have to label that too. And then this would be AC, right, or V squared divided by R, and then the specific would be R2. All right, so now if I'm trying to set this up, we know, hopefully, that we have that thing called the universal law of gravitation. So Fg is big G, M1, M2, all over R squared. Quick review. Big G, gravitational, universal law of gravitational constant, known, no big deal. M1 and M2 are the two masses we're talking about. In this case, it would be the satellite and the planet would be the two things. And then R is the distance between the center of those two objects. So if I were to sub this in here, I would have big G, and it'd be the mass of the satellite. Cool. Mass of the planet would be the other mass divided by, and this would be R2, right? Because that R2 is, it's the distance. But just in this would be squared, and that looks weird, 2, right? And then this would be equal to mass of the satellite, right? And then this is V2, we could label this. We want to be careful, V2. Divided by R2, and then don't forget that this V2 is squared. A lot of 2. So if I'm looking to clean this up a little bit, which we normally are in these type of problems, you can see that hopefully the mass of the satellite should cancel. And then one of these would actually cancel with that. So what I'm left with here is that big G, mass of the planet, divided by R2, is equal to V2 squared. I don't have to go any further to realize that I have a problem, okay? And the issue I have here is no big deal. Big G is a known value. We can look it up if we forget it, but we got that. R2 is given to me in the problem, also not an issue. The problem that we have is with the mass of the planet. Looking at the question, it's not given at all. Yikes. So I need it. Right, there's no way for me to solve this, and because like realistically, to solve, I think we kind of understand that I would square root both sides, right? But there's no point in me really going much further than that because I need to know the mass of the planet. Don't we know a lot about the first satellite, though? Like, a lot about the first satellite. Because if you think about this, and here's where we're gonna break into two separate ways of doing this, right? There's the continue down this path, and then there's the hey, let's cycle back to the beginning. So, but let's continue down this path. We're already on this path. FNet1 would be FG1, like acting with the first satellite. But the first satellite is also in circular motion. So FG1 would be V1 squared over R1. And then this would be big G, mass of the satellite, mass of the planet, divided by R1, and that would be squared. And then this is mass of the satellite, V1 squared, all over R1. So, boom, boom, just like last time. Boom, boom, just like last time. And I'm left with big G, mass of the planet, divided by R1 is equal to V1 squared. Multiply both sides by R1, right? R1. R1. Divide both sides by big G. Divide by big G. And now I have the mass of the planet. Just V1 squared times R1, all divided by big G. And going through this, right? V1 given to me in the original problem, right? 6.36 10 to the 4 meter per second. R1 given to me in the original problem, 2.11 10 to the 6 meters. Done. Big G, 6.67 10 to the negative 11 Newton meter squared per kilogram squared. Oh, that's just a little cut off, huh? Pause. I'm back. It's fixed. You can look at it, right? So now, if I did this, right, I would have the mass of the planet. And then, couldn't I take this mass of the planet and punch it in there and have my V2? It's like a pretty good plan to me, right? And I'm not going to plug in the numbers, right? That's like for you guys to do that. But that's the strategy here. Now, I got stuck, right? If we circle back, I got stuck here, right? Is basically where I got stuck, and I didn't give up. I didn't freak out. Notice that if you're given information about a bunch of different things, there's probably for a reason. It's pretty rare in our problems that we do that I give you extraneous information for absolutely no reason, right? So that's pretty common that we have these things for a reason. Yeah. So like, yeah. Now, is this a little bit of work? Yeah. I mean, if you look, you're basically doing the same thing twice, which is a bit of work. And if you'll notice, we would do this. Let me just change the color quickly. This second half stuff that we did here is what we would do exactly for part C. So exactly this is how we would solve for part C. Everything exactly as that's laid out is how I would solve for part C. And then you're challenged in E that, like, did you have to do this, right? Did you have to do this way, right? So let's cycle back to try to figure out was there another way, right? Was there something else to do? Was there another way to do this? Or truly was this the only method? Is there anything wrong with this method for solving this problem? Absolutely not. Nothing. However, does this take a lot of time? You'll see I'm at 9 minutes doing this, right? And that's me. So I'm gonna take a bit of time here. So let's think. Let's roll this out of the way. Let's go back to the original scenario and think a little bit. Now, it's still true for both of them that FNet1 is like FG1, right? And we could also say that FNet1 would be like mass of the satellite, and this would be like AC1, I guess, right? But it's also true that, right, like FNet2 is FG2, the force of gravity in the second satellite. So then FNet2, right, is mass of the satellite AC2. Now, when we're given two things, it's pretty common that there's some relationship between them. And if I look at my distances, you might notice something, because R1, right, is given as 2.11 times 10 to the 6 meters. Meanwhile, R2 is conveniently 8.44 times 10 to the 6 meters. If you look at those, how interesting that R2 is actually 4 times R1. How suspicious that it's exactly 4 times. How suspicious. It's not suspicious. That's the point of the problem. If you remember, something we talked about a bit, that we're continuing to talk about, FG, big G, M1, M2, all over R squared. The big deal about this equation is that FG and R are what we call an inverse square relationship. So whatever happens to R, the inverse square of that is what happens to FG. So if you double the radius, inverse square, well, 2 squared is 4. The invert of that is 1/4. So by doubling R, I would actually get 1/4 of the force value. So if we look at what's going on here, well, 4 times the radius, right? So that means 4, right? 4 squared is, let's think, 4 squared. That's a game, right? 4 squared. Oh, 4 squared. Sorry, I forgot the is 16, and invert that as 1/16. So what I could say, right, and there's 2 ways to write this, and there's a convenient way and a not so convenient way, would be that FG2 is actually 1/16 of FG1, or the other way, which I like maybe a little bit better, is that FG1 is actually 16 times bigger than FG2. It's a little bit of a trick. Recognizing that the distances are like that. But this is the key. Because of all of this stuff. Because now I have a way that I can relate the two. Because if you look, we think about mac and cheese, right? M, V, and R. M I don't have, but it's the same for both. I have both of the R's and only one of the V. So what I can actually do now is basically smash in here, because FG1, right, is really like F net 1 16 times. FG2 is really like F net 2. And we had said that F net 1 would actually be like, well, the mass of the satellite, AC1, 16. F net 2 would really be mass of the satellite, AC2. Satellite, your mass is gone. So I got V1 squared divided by R1 equal to 16 times V2 squared over R2. Subbing in for AC. Now, if we look there, I have 4 variables, and I know all of them except one. So all I really have to do here is let's go to town and simplify. So let's do that. I'm gonna do another step though, because you know me, right? The additional step that I'm gonna take is the following. I know this, that R2 is actually 4R1, so I can also write this. And I guess maybe I won't scroll. I'll just take this work up to here. I can write this as V1 squared over R. I'm doing in terms of R1 or R2. That's fine. R1, and then this is 16 V2 squared, and then this is actually like 4R1. The benefit to me doing this, you might say, well, I know those numbers. Why would I do that? Because adios, muchacho, can actually cancel out the R1. So that's actually the benefit of me doing that. I can cancel that out. And again, I'm trying to solve for V2, right? So 16 divided by 4 is 4. So I got V1 squared, and this is 4 V2 squared, right? So what I would do here is I would actually divide both sides by 4. So you could write this as 1/4 or whatever you want to write this, right? But I have that v1 squared over 4 is equal to v2 squared. This is where I would have to square root both sides. And I'm making sure to put I put the little hook on the square root just to make sure that that's going. But so now I'm going to get v1, and 1/4 under the square root actually ends up being 2. So I'm actually going to end here that v2, right, is just v1 divided by 2. And now at this point, I know that I knew earlier that v1 was 6.36 times 10 to the 4 meters per second divided by 2. So I'm going to get here that v2 is 3.18 times 10 to the 4 meters per second. Bing, bam, boom. Yikes. It's one heck of a problem. And then part B is just saying like order of magnitude means power of 10. And if you look at these two, they both have the same power of 10, which would make sense. If one of my numbers was enormous, right, 10 to the 11, 10 to the 46, that'd be sort of weird. They got to be in the same ballpark, same neighborhood. So I'm happy with this value, and it's the same exact number you would get going the other way. For those of you that are curious, that would do some solving, that don't want to check the answer key, the mass of the planet, if you do that, is 1.28 times 10 to the 26 kilograms. And if you're curious in terms of, for us, the Earth is actually 5.98 times 10 to the 24 kilograms. So this is about 21.4, 21 and a half times larger than Earth, which is fine. So we got two ways of doing this, right? We got the trick, right? And then we have the other way, which is a little bit more grind method, but still certainly sufficient and does work nonetheless. Now, what would I take away from the trick here? What's the big thing to recognize? Because obviously a problem like this in its entirety might be a bit big for an assessment. But what I would look for is trying to identify times when we have this. When we have that this distance and this other distance are some exact proportion to one another. Also, when you're given more than one thing, there's a reason we're given more than one thing. Not to ignore one of them, it's to understand both of them to their fullest, to the max. So this coupled with the PDF answer key, I hope this helps you out a whole bunch. You have to be able to do, I would say, got to be able to grind through this. Not that bad. You have to do what's in blue anyway, either way. So it's not too big of a deal doing a problem out of order, right? Not a big deal. This trick, those of you like reaching and trying to be the best you can be, it is important to recognize that the distances can be slightly different. Great. Hope this helps out. Good luck, happy studying, and until next time, kiddos.